Right, apologies for the sound on the last one. I think I might have sorted it now, hopefully anyway. So anyway, in the previous video we had a bit of an introduction to simple harmonic motion. We revised what we meant by oscillations and we linked that to waves and circular motion. So I showed you that a rotating radius at constant angular velocity gives me a sine wave, which is the same pattern we might get for an oscillating mass on a spring, for an example. So let's define what we mean by SHM. It's got a very specific definition and you'll be expected to remember it for A-level physics and be able to state them often for 2-mark questions. So there are 2 conditions that need to be met. The first is that the acceleration of the object has to be proportional to the displacement from the equilibrium position. That'll probably make more sense once we have looked at some examples. Okay, so that's it. Condition 1, and then condition 2 is that the acceleration has to be back towards the equilibrium position. So if you think back to the mass on a spring, which we'll be looking at again in a minute, if I displace it downwards, then there's a force accelerating it upwards in the opposite direction to that. And the more I displace it, the bigger the force upwards. Okay, so assuming the spring is obeying Hooke's law, then the restoring force is proportional to the displacement. Oh, just notice I spelt displacement wrong. And it is back towards the centre. If I pull it down, then it's going to accelerate up. If I lift it up, it'll accelerate downwards. Right, so what does that mean? If we look at that mathematically, we can say that the acceleration is proportional to minus x, where x is the displacement, a is the acceleration, and the fact that it's minus is because it's in the opposite direction. If x is positive, then acceleration is negative. If we put that as an equality, it turns out that the acceleration of a simple harmonic oscillator is equal to minus, same reason, omega squared x. And remember that omega squared in this case is not really to do with circular motion, it's to do with the time period, like I showed you in the previous video. So if you're not sure what that means or where that comes from, have a go back to the previous video and remind yourself. Right, next thing then, why is omega squared the constant in that equation? Well, you don't really need to know the derivation for A-level physics, but I like to show you, and we're going to do it 2 ways. First way, without using calculus. So if you don't do maths, this is the way to think about it. If you do maths, then the calculus way is a little bit shorter and a little bit easier to understand. Right, so previously we're going to circle, and if I draw that horizontal line there, so this is my equilibrium position, which I'll carry on over there. Looks like it's going to be Pac-Man, doesn't it? It's not. And we have a radius at an angle theta, and that angle is increasing at omega radians per second. Last lesson what I did was I plotted this height over time, and we ended up with a sine wave. Instead of plotting that, if I just kept it all in the same place, then this point would have gone up and down and up and down and up and down sinusoidally, with that being the equilibrium position. And its acceleration would always be towards that equilibrium position, because the acceleration of an object undergoing circular motion is always towards the centre. Okay, right, so we should know that the acceleration of an object in a circle is omega squared r, or v squared over r, but this is the more useful version for the moment. We're interested in the component of the acceleration in this direction, or this direction. So we'll look at magnitudes initially, and we'll worry about direction later. So if you look at the extreme position, where the radius is round to this point here, then the acceleration, the component of the acceleration in that direction, is the whole of that. Whereas here, the component of the acceleration, which is in this direction, is 0. The 0 component in the vertical direction if the acceleration is horizontal. So we're going from 0 to maximum as the angle increases. That should suggest, in fact, this is the component, isn't it? This is the component here. So the acceleration is omega squared r sine theta, to take the component in the vertical direction. So the acceleration of the object projected across here is equal to this. Okay, at the centre it's not accelerating at all, and at the extremes it's accelerating with this value here. Okay, but we also know that this term here is the displacement from the equilibrium position, this height here. So we can replace that with A equals omega squared x. Now where does the minus come in? Well, when the displacement is up this direction, the acceleration is the other way down. So we have to invert it to make the direction of this and the direction of this the opposite way around. Okay, so the negative is just there for a direction. Right, let's look at it with calculus. This is a bit quicker. So we know that the displacement of an object is r sine theta, and we also know that the velocity of the object is dx dt, and if we differentiate that we get, oh hang on, I missed a step. We also know that the theta is omega t, just as distance is velocity times time, the angle is the angular velocity times time, so we can replace that with r sine of omega t. So if we differentiate that with respect to time, then we get r, omega comes out, differential of sine is cos omega t, and then the acceleration of that, so dx d2x dt squared, second differential of x is the acceleration, so this is velocity equals that, acceleration equals that. Then we differentiate that again, we get r omega stays there, omega comes out, so we get r omega squared, and then the differential of cos is minus sine, so we go minus sine theta, and as before we said r sine theta was x, the displacement, so we got minus omega squared x. Okay, so if you didn't follow that, don't worry, because you don't need either of those derivations. It's just proving that omega squared is the necessary constant to make the conditions of simple harmonic motion an equality rather than a proportionality. However, what we do need to know is that if we've got an equation of a movement of an object in this form, okay, so if we can prove that an object has acceleration in that form, then it shows that it's a simple harmonic oscillator, and that's what we're going to do next. So here we've got mass on the spring, and this is the equilibrium line, so at this point here the tension is equal to mg, those two are balanced, but I apply an external force temporarily and I pull it downwards, and I pull it downwards a displacement of x, and the tension therefore increases, the mass stays the same, and when I release it we've got a resultant force upwards of the new tension minus the weight. Now the increase in tension will be proportional to this displacement, won't it? Because we know that F, for a spring, F equals kx, where x is the extension, k is a spring constant. So the tension upwards will be the initial tension, T, which is equal to mg, plus this extra little bit. Mg is acting downwards, so that will cancel that part of the tension, and we're just left with a resultant force acting in the upwards direction accelerating upwards. Now we need to define a direction, so let's say downwards is positive, because we pulled it downwards in the first place. So our x is positive, but our acceleration is negative. So actually, we've got the force, the accelerating force is minus kx. Okay, by a similar argument, if I lift it up, a displacement of x, assuming the spring is still in tension and it hasn't gone slack, then I've reduced my tension by kx, and I have a resultant force downwards of plus kx. So my resultant force is equal to kx. But because my displacement was negative, I still need that negative sign there. I've got a positive acceleration downwards, but I've got a negative displacement. So negative multiplied by the negative gives me the positive value of there. Okay, so we've proven that the resultant force acting on this spring is proportional to minus x, which is what we kind of wanted, but what we need to do is prove that the acceleration is proportional to minus x. Well, that's fairly easy, because acceleration is f over m from f equals ma, and so we can say that the acceleration of a spring is equal to minus k x over m. If we take the x out, because that makes things a bit more, then that is in the same form as a equals omega squared x. Forgot the minus sign, so I'll just put that in. Now, if we look at this, omega squared can be compared to k over m. So in the case of a mass on a spring, our constant is k over m, where k is a spring constant, m is the mass of the mass of the thing on the end. Right, where's that? Why is that useful? Let's go for a different colour pen again. Right, why is that useful? Well, it means we can find out the time period of this in relation to the spring constant and the mass, because we know that omega is 2 pi over t. 2 pi radians in 1 revolution, t seconds to do 1 revolution. That's what that is. Okay, but we also know now that omega squared is equal to k over m. So we can say, if we square all that, no, let's not do that, we'll square root this. So if omega squared is that, then omega is the square root of that. So if I invert that, t over 2 pi is equal to the inverse of this, which means that t is equal to, take 2 pi over to the other side, 2 pi square root m over k. So by using basic physics, you use Hooke's law, Newton's laws at F equals ma. I know it's strictly not Newton's law, but it comes from Newton's law. And our understanding now of simple harmonic motion, we have derived how to calculate the time period of a mass bouncing up and down on a spring. Okay, and there's a required practical that you need to do to prove that is the case. If you've played with the simulator that I showed you last lesson, then you can prove it in that as well. Obviously it doesn't really prove it because the simulator's using the maths that we're trying to prove, but it kind of proves it. But you need to do it for real anyway when we get a chance to do our required practical. Right, let's have a look at it graphically. Look at the same thing graphically. So we've got the oscillator, displacement's following a sine curve, and we should know that the velocity of an object is the gradient of our displacement curve. So if I draw these lines, then I'm going to plot a point where the gradient on this would be. Okay, so here we've got a high positive gradient. Now the value of this, we'll work that out in another lesson. We know that the maximum displacement is the amplitude, and the minimum displacement, or maximum negative displacement, is minus the amplitude. So I've put those on. And we also saw in the previous slide that the acceleration was equal to omega squared x, and the maximum acceleration, minus, the maximum displacement is the amplitude, so the maximum acceleration will be omega squared a, where a is the amplitude. Right. I'll show you how to figure out the maximum velocities in another lesson. So if we move this line along and plot a point where the gradient is, okay, so in this case the gradient is 0 on the displacement graph, and here it's high negative, maximum value negative, and here it's negative again, and here it's maximum positive, and we get a cosine curve. Okay, so if you were following along the calculus method of working out y as omega squared, then that's what, so the velocity followed a cosine curve. Do the same for the acceleration. Well, the acceleration is the gradient of the velocity graph. So here the velocity gradient is 0, so we've got 0 acceleration. Velocity gradient here is maximum negative. Velocity gradient here is 0, maximum positive, and 0. So we get an inverse sine curve. Well, actually that's what we wanted, isn't it? Because our acceleration is minus omega squared x. It's negative of our displacement curve.